In this section, we're going to use linear programming, which is what we've been doing up to this point already, in order to maximize or minimize an objective function. Now, we'll minimize it or maximize it based upon various constraints, which we think of as inequalities. For example, if it's a cost function, we might like to minimize costs. So we'll minimize a cost function while we might want to maximize a profit function. All right, well, let's look at a simple example. I've done some of the work for us in this example. In this case, I want to find the maximum and the minimum values of this objective function. This could represent a profit function or a cost function. We're just going to label it with a z. So we're going to find the maximum value of z and the minimum value of z based upon some inequalities, which I have already graphed. So we are looking at these two lines, and we're looking at the lower half plane, and we're looking at only the quadrant number 1. So this, I'll shade it a little bit more, is the region in question. This would be called our feasibility region. I've already done that hard work. So remember that the minimum and maximum points always occur at vertices, or corner points, of this feasibility set, of the solution of the inequalities. This is a four-sided solution set, that side, here, and here. And I've circled the four corner points. So let's write down here each of these four vertices or corner points. I'll start with 0, 0, this one right here. And then this one would be 0, 1, 2, 3, 4, 5, 6, 7. This one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, comma 0. And the fourth one, this one right here would be 2, 3, 4, 5, 6, 7. 7, comma 1, 2, 3, 4, 5. Okay, so we have listed all the vertex points. And I mentioned earlier that the minimum and maximum values of an objective function, based upon inequalities that gave us this region, will always occur at a corner point. So we need to compute the value of z based upon this xy pair. Well, this one's very simple. That's 0, 0. If x is 0 and y is 0, then z is 0. So the value of z is 0 there. Now, if x is 0 and y is a 7, we would get 5 times 0 plus 14 times 7. And that is 0 plus 98. All right, so we got a 0 for the first one, 98 for the second one. And z for the third one would have a value of 5 times 14 plus 14 times 0. 5 times 14 is 70 plus 0. So we get 70 for the third one. And the final one, the fourth one, this point right here, ordered pair 7, 5, would give us a z value of 5 times 7 plus 14 times 5, which is 35 plus 70, which is 105. So we look at all four of the values and find the minimum. Well, that's easy. Here's the minimum value. The minimum value of z is 0, and it occurs at this vertex point, the origin, 0, 0. 98, 70, 105 is the maximum possible value for z, and it occurs when x is 7 and y is 5 at this point right here. So the max point occurred there, the minimum point occurred there, the minimum value is 0, the maximum value is 105. Okay, the next example. we want to minimize a cost function defined right here. Minimize C, subject to the following constraints. I don't have a whole lot of room, so I'm going to do some of the work in my head, but you should go through and work every bit of it out. All right, we have all these inequalities. These ones are the simple ones. X greater than or equal to 0, y greater than or equal to 0 just means that we're only in quadrant number 1. So this is going to be our origin right here, 0, 0. Okay, the first line, first inequality, we start with the line x equals 6. That's a vertical line, and it would be 1, 2, 3, 4, 5, 6 right here. That's the vertical line, and we're only in quadrant number 1, so I'm not going to extend it below here. And would this be a left? Yeah, this would be a left half plane. Remember, when you have a vertical line, you don't have an upper half plane and a lower half plane. It's either left or right. And if x is less than or equal to 6, less than or equal means go to the left. So I'm not going to shade it yet, but we would be, the solution to just that one inequality would be shading everything to the left of that line. The next one, well, it's going to be, let's first graph the line. Let's assume this is an equal sign and graph the line with a solid line because it's got the equal sign. And this would mean y less than or equal means we would shade the lower half plane. But the line is y equals 1/3 x plus 4. So 1, 2, 3, 4 is the y-intercept. And the slope of this line is 1/3. So go up 1 to the right 3 from this point. Up 1 to the right 3. Up 1 to the right 3. Up 1 to the right 3. Okay. And so far, remember, we would shade to the left of this and the lower half plane of this, so below that. So far it looks like it's this region with 4 sides, but we have one more inequality right here. Now this line would be y equals negative 2/3 x plus 4. So it has the same y-intercept as the other line, and the slope is negative 2/3. Go down 2 to the right 3. Down 2, 1, 2, 3. Down 2, 1, 2, 3. So it looks like right, oops, not very straight, but that's the line associated with this inequality. So if I were to label just the lines, we would have L1 as that vertical. L2 would be this line. And then L3 would be this line. Okay, so in this line we just drew, it's y greater than or equal. So this one would be an upper half plane. This was lower half plane. And so what region? There's one region in this graph that's to the left of this line. It's below this line, and it's above this line. And yes, I'm sure you guessed it correctly, this triangle, just like that. So this is our feasibility set, or the solution to the set of inequalities. And now we take the corner points from that feasibility set, and we plug it in to this to figure out what the cost would be here, here, and here. So let me make a little table like we had above. I'll put the vertex and the cost function. All right, this vertex is 0, 1, 2, 3, 4. This vertex is 1, 2, 3, 4, 5, 6, 0. And the third vertex would be 6, 1, 2, 3, 4, 5, 6. We want to minimize the cost function. All right, so let's see what the cost function is with x equals 0 and y equals 4. X equals 0 means we get a 0 here. 6 times 4 would be 24. That would be the cost using this point. Then 6, 0 would mean x is 6. 5 times 6 is 30 plus 0. 6 times 0 is 0. 6 times 5 is 30. Finally, we get a 6, 6. If x and y are both 6, we get 5 times 6 is 30. 6 times 6 is 36. So that would give us 66. So we're trying to minimize the cost. So we look for the smallest number. It looks like it's right here. That's the minimum. So we would say that the very minimum cost is going to be 24, and that cost, the value of 24 occurs at this point right here, where x is a 0 and y is a 4.